All right, nerds. Today we start a new chapter. Feels like forever since we've even done any notes. But today we're going to start chapter 4. We're actually going back to chapter 4. Chapters 4 and 5 are all about polynomials. Lots of graphing, lots of factoring, lots of stuff that we talked about at the very beginning of the year in chapter 1. Properties of our graphs. Where they cross the x-intercept, or where they cross the x-axis, where they cross the y-axis, where they're increasing, where they're decreasing, domain, range, maybe symmetry, all kinds of things like that, coming up from way back in chapter 1. But here it is, chapter 4, section 4.1, polynomial functions. First of all, what is a polynomial function? A polynomial function is any function that is held together with pluses and minuses where all of our x's have exponents on them that are positive whole numbers. Okay, but that doesn't say anything in there about it being positive whole numbers, so let's write that first of all. All exponents of x are positive whole numbers. So held together with pluses and minuses, and every exponent on an x is a positive whole number. Now, all the things that we're holding together with these pluses and minuses are known as terms of the polynomial. And we could even count the terms if we wanted to. If it is written so that the degrees, the exponents, are counting down from biggest to smallest, and this one at the end wouldn't even have an exponent on an x because it doesn't have an x. Technically, it's an x to the 0. So if they count down from biggest to smallest, we say that that polynomial is written in standard form. Are all polynomials written in standard form? No. Should they be? Yes. Okay. Why? We'll get to that in a minute. The numbers that sit in front of our x's are known as coefficients. I think you guys all know that term already. And this is why it is important that they be written in standard form. Because the term that has the highest exponent, the biggest exponent, that term is your leading term. That should have been the leading term. It should have been written in the front. The coefficient of that x would be known as the leading coefficient. So this a sub n would be our leading coefficient, and the biggest exponent would be the degree of the polynomial. So if it's written in standard form, that biggest exponent thing written first, that biggest exponent is the degree of the polynomial. So you can have third degree, fourth degree, fifth degree polynomials, sixth, seventh, eighth, ninth, 17th degree polynomials. It's whatever the biggest exponent was. Okay? And that term should have been written in the front, and the coefficient that sits in front of that is called the leading coefficient. The leading term is a big deal. It tells us the degree, and it shows us the leading coefficient. Because if you know the degree and you know the leading coefficient, then you can tell me what the end of the function looks like. We call this the end behavior. So you'll notice in these pictures, there's solid lines and there's dotted lines. The dotted line is representing a piece of the graph that we wouldn't know. I like to call it the spaghetti in the middle. Our leading term will always tell us which directions, which two directions, our endings point. And they could be going different directions or the same direction. And again, all of this is determined by that leading term. So we need to look at the leading term. So what makes our endings point different directions? Odd degree. If you have an odd degree polynomial, your endings point opposite directions, one up 1 down. 1 up, 1 down. If the leading coefficient is positive, it looks like this. So the positive leading coefficient goes left down, right up. A negative leading coefficient gives us left up, right down. Someone in first period asked me, well, how would you know that that's how that worked out rather than just trying to strictly memorize it? How could I possibly know? And I say, well, that's always a good question. The how do you know is always a great question. Let's call this our roller coaster car. Let's say we started here and we're going to end over here. Is this an overall upwards trip or overall downwards trip? It's an overall upwards trip. Basically, if you wanted to imagine you connecting the arrows with a line, does that line have a positive slope or a negative slope? Positive slope. Positive leading coefficient. We call this the average rate of change, the average slope of this graph. The average slope is positive. So overall upwards trend. Whereas this one has an average rate of change, the average slope of the curve beginning on the left and heading to the right. That roller coaster has an overall downwards trajectory. Yeah, sure, it might come up a little bit, but overall it's a downwards trip. Okay, so this line that I just drew has a negative slope. That means this curve has an overall average slope that is negative. Leading coefficient is negative. So then what makes the endings point the same direction? Well, the graph that you know of where the endings point the same direction is a parabola, right? Either both up or both down. And what is the degree of a parabola? What's the exponent? The biggest exponent in the equation of a parabola? 2. 2 is an even number. So if you have an even degree polynomial, your graphs point the same direction. I'm just going to write poly instead of polynomial. And if you can recall back to towards the beginning of the year when we were talking about quadratics, graphing our parabolas, I said to you many, many times, positive people smile and negative people frown. Think of that as their endings. These point up. Positive people smile. It's got a positive leading coefficient. Here, these are your endings. Negative people frown. The leading coefficient is negative. So I have a positive leading coefficient. For that one, and this one, a negative leading coefficient. What about the spaghetti graph in between the endings? That's for later in this chapter. Maybe next chapter, I'm not sure yet. Right now, we're discussing what the endings would look like and how we would know that. Comfortable with that stuff? Okay with that knowledge? Alrighty, so we've talked about what it means to be a polynomial, the exponents of this thing that's held together with pluses and minuses, when all the terms are held together with pluses and minuses. The exponent on the x's must be positive, and they must be whole numbers. And we use the leading term, meaning the one with the highest exponent, to tell us the degree of that polynomial. And then we look at the leading coefficient to see if it's positive or negative. And between the degree and the positive or negative front number, we know which two directions our endings point. Now, in the images, we have limit notation describing that. So whenever I give you the instructions of describe the end behavior, we'll be using the limit notation. The only other information that's on the front of these notes, is this picture right here. Now, mine's in color, yours is not. And it's kind of hard to see the two differences here. One is blue and one is green. I wanted to print it in color, and I did this for all of my classes that are learning this material today so that you can see what's happening with a parent function. So these two are the odd degree parent. We call it a monomial instead of a polynomial because it's one term. So that's x to the second, x to the fourth, x to the sixth, x to the eighth, so on and so forth. Positive or negative doesn't matter. I needed you to know what happens to the graph as the exponents grow. X squared is the red one. X to the fourth on my paper is blue. It's the next one. That's that right there where I just put that dot as blue. But after this intersection point, the blue one's here. Then x to the sixth is this green one. But then after the intersection point, it's right there. They've changed places. And what I'm needing you to see is as the exponent went up, this zone between the intersection points, the graph gets flatter and flatter and flatter around 0. But then after the intersection points, so if I just like cover up that part, the graph gets steeper and steeper and steeper as the exponent grows. Same thing is true for this one. Why is that happening? Well, if you think of your exponential function knowledge, if you take a number between 0 and 1, like 1/2, and you square it, you get 1/4. If you cube it, you get 1/8. If you raise it to the 4th power, you get 1/16. Notice, as the power went up, the number got smaller. That's literally why it's flattening out, because you're raising a small number to a power, crashing the number closer to 0. But then after this intersection point, which by the way happens at x equals 1 and x equals -1, anytime you raise a number that is bigger than 1 to a power, and that exponent gets bigger and bigger and bigger, your values get bigger and bigger and bigger, which means it gets steeper and steeper and steeper until it's almost vertical. It'll never be vertical, but it looks that way. All of these kinds of graphs, as long as they're monomials and there's no other x's put anywhere and they haven't been shifted left or right, will have even symmetry. They'll be symmetric around the y-axis. So these, the way they're drawn, these monomials, even degree monomials, have even symmetry. They also have a vertex, just like the quadratic does. They all have a vertex, supposed to be at 0, 0. And that is why this range is not all real numbers. But you'll notice the domain is all real numbers. That's because you can raise a number to any positive power you want, and you'll never get in trouble. In fact, that's true for odd degree polynomials as well. As long as you're dealing with real numbers and you're dealing with whole positive exponents, you can raise a number to any whole positive exponent you want. The domain of every polynomial is the same, all real numbers. Because these endings are both up or both down, though, we do have a restricted range. This vertex is at 0, 0 and then goes up. So the range is from 0 to infinity. This vertex is at 0, 0 but then goes down. So the range is from -infinity up to 0, and the bracket means includes that number. It's important that you know that polynomials will never have any asymptotes at all, because by definition, an asymptote is a line that a graph will get infinitely close to. Polynomials do not have asymptotes. They're just wiggly lines, okay? Now, odd degree polynomials, since we're already talking domain and range, let's keep talking about it. We've already said the domain is all real numbers, but because we have one ending up and one ending down, and the spaghetti better connect those endings, the range of odd degree polynomials is all real numbers. So these have really easy domain and range, all real numbers. Same thing occurs with these between the intersection points. As the exponent gets larger, the graph tends to flatten out around 0. But after the intersection points, as the exponent gets larger, the graph gets more steep. Okay? And just to bring back our old knowledge, these both have odd symmetry. Reflecting over the x-axis, so turning upside down, is the same as reflecting over the y-axis, turning left-right. Doesn't make a difference. If you flip these upside down, or if you flip them left-right, you'd get this image. And since reflecting them either way gets you the exact same answer, these have odd symmetry. Does that mean all odd degree polynomials have odd symmetry? No. they have to have their, if you remember the terminology, inflection point at the origin. All odd functions, odd symmetry things, are centered around 0, 0. Just like all even things are centered around the y-axis. So that's all old knowledge. Old knowledge. Decreasing to the left, increasing to the right. Increasing to the left, decreasing to the right. Technically, always increasing. Technically, always decreasing. According to AP Pre-Calculus. So I'll teach you the same thing. Because some of you will be going to AP Pre-Calculus next year. So as long as you know that even degree monomials have their vertex at the origin and either point up or point down, you're set. As long as you know that odd degree monomials are centered at 0, 0, and you know which way they go, you're set. For now. Would you like to ask me any questions about all of the information that's on this front page before we do any practice? It's not too bad, right? Not too bad. So what are we doing first? Well, first we're going to describe our end behavior using limit notation, as well as find domain and range. Okay. This is only one term, so I think we can all see what the leading term is. It's right there. So the degree, what is the degree of this monomial? You guys can just shout it out. Class, what's the degree of this monomial? 4, good. Degree of this monomial is 4. Is 4 even or odd? Yeah, this is an even degree monomial. The fact that it's even tells me something about its endings. I'll ask that question in a moment. The leading coefficient, is it positive or negative? What is the leading coefficient? It's -3. So it's negative. So we have a negative leading coefficient. We have an even degree monomial. So first question, class, lots of voices. Since the degree is even, are my endings going same or different directions? Go. Same directions. Good. And because the leading coefficient is negative, is it both up or both down? Both down. So I don't know both down because it's negative. Remember, negative people frown. So we have two endings that point down. Don't worry about what's going on in between them. You know this is what the left and the right of the function looks like. Limit notation. The limit as x approaches negative infinity of f of x equals negative infinity. So I've written limit notation a lot in this class, and I just realized this morning that I've never written down what this says. I've said it a bunch of times. This says, as my graph goes left, so as I go left on my x-axis, on my y-axis, I'm going down. So here's the words. This is left, and this is down. Left is negative infinity, down is negative infinity. That's literally what this tells you. It's like a set of instructions. Go left, go down. This one says go right, go down. Positive infinity is to the right, but negative infinity is still down on the y-axis. So that says go right, go down. And as far as the domain is concerned, it technically is a polynomial, and all polynomials have the same domain. All real numbers. But because this graph has both endings pointing down, this graph will have a maximum somewhere in between them. And since it has a maximum, an absolute maximum, the highest possible point it could have, we have a restricted range. Now, normally you wouldn't know the range without the whole graph, but it's a monomial that has not been shifted up or down. That means it has that range right there. Negative infinity up to 0 inclusive. Boop. Like so. Oh, crooked paper. And if you have any questions at all about that example, air it out. Let me hear it. What can I help you with? What can I do? What can I explain? I'm going to be real with you guys. I really want last chapter's success to continue because it was a very, very strong showing of your guys' skills. I'd like for that to continue into the future. So please talk to me and please ask me questions if you have them. No, the bracket is because we actually hit this y value. Can't go any higher than that. Nope. Parentheses mean we can't reach that. And since infinity is not actually a number, we can't reach it. In the exponentials chapter, we had a horizontal asymptote for things, like this. Let's just say that was the x-axis. We would get infinitely close to it, but never actually hit it. So this thing's range would have looked like this. And let's just say that was at the x-axis, because we weren't actually hitting that x value. Whereas this graph's vertex is, I said y value, excuse me. This graph's vertex is literally at that coordinate. So because it actually achieves that y value, we bracket that y value. Same thing for the one that we just did. Let's do one more of those just to really drive it home. This one says 3x to the 5th. The degree of this polynomial, class. What's the degree of this monomial? 5. It is degree 5. And class, is that an even or odd number? Odd number, great. And my leading coefficient, is it positive or negative? Positive this time. The fact that it's a 3 just is a vertical stretch. It's a vertical dilation. We don't care about that. We'll really care about, was it positive or negative, and we see that it's positive. Oh, since it's an odd degree polynomial, I know it's a monomial, but because since it's odd degree, it is a very easy domain and range, all real numbers. And that's because the odd degree polynomials are not like the even degrees. Their endings do not go the same direction. Their endings go different directions. Tell you what we'll do. I'll draw the two options, and then as a class, we'll say left or right. Okay? This way I could really get a feeling for what we're doing. So is it or is it? So class, on the count of 3, what I'm looking for is you to shout out left or right. Because this is a positive number, 1, 2, 3. Lots of people said left. Lots of people, I 100% agree with you, because overall upwards trend, a positive rate of change. So this is definitely not what we're going to deal with. Oh, it was like the worst X ever. There it is. So let's write out our endings. Going to the left, the limit as x approaches negative infinity, meaning as I head left, my y values head down to negative infinity. So that's left and down. But this one here, that's right and up. The limit as x heads to positive infinity, because that's what's at the far reaches of the right side of f of x, is upwards to positive infinity. So this is right and up, like that. There. What do you think? Identifying end behavior. Identifying end behavior using limit notation. Identifying the degree. Are all of these things easy enough? Nice little baby steps for this chapter. Yeah. Okay. Sounds good to me. Let us go ahead and sketch this cubic. Now, I could have given you more x values, We'll just do more x values verbally. But for now, what are we going to do? Literally take these numbers and plug them into x. If you need to, use a calculator, whatever. -1/4. And then I have times -2 to the third. This is 3 negatives and 1 more negative, so 4 negatives. If I multiply 4 negatives, do I get a positive result or a negative result? An even number of negatives is always a positive result. So if you type this on your calculator just right, you will get a positive result. 2 to the third is 8. 1/4 of 8 is 2, so that happens at +2. Again, if you want to use your calculator, that's fine. But here I'm seeing 4 negatives. 1, 2, 3, 4. That means positive result. And 1/4 of 4 is 1/4. 1/4 of 0 is 0. This monomial is centered at 0, 0. It has its inflection point at 0, 0 because it has not been shifted up, down, left, or right. That makes this an odd function, which means these y values will repeat, but they'll be negative this time. So this will be a 1/4 and this will be a 2. But if you didn't believe it, you could just grab handy dandy calculator and you could plug it in. You go, okay, 1 to the third power is 1, and -1/4 times 1, oh, that's -1/4. And you could do the same thing with the 2. 2 to the third is 8, and 1/4 of 8 is 2. Oh, but it's -2. On your homework, I've made the boxes large enough so that way you can show me you plugging the numbers in. I don't want to hear, I did it in my head. I don't want to hear, I did it on my calculator. I want to see what you typed on your calculator. I want you to write it down. Because as usual, I'm going to give you the answer key. So if you just draw my graph, I'm going to assume you just took points off of my picture that I put on the internet. Okay, let's see. We've got a 0, 0. We've got 1, -4. 2, -2. I've got -1, +1/4. -2, +2. And let's get some more points, just for funsies. Let's use 3. 3 to the third is 27. 1/4 of 27. Well, what's 1/4 of 28? 7. So this value, 1/4 of 27, is just a little bit less than 7. But it's negative. So a little bit less than -7. So 2, well, when you say less than, you mean, the point is, it's going to be like -6.75, I believe. Yeah, -6.75. So I said less than 7, but I meant like not as far away from 0 as -7. So like right there. And if you use -3, you'll get positive almost 7. Like this. So it gives you a pretty good idea of what this thing looks like. Like that. And believe it or not, that is much shallower than the standard x to the third graph is. Because 1 to the third is 1, but 2 to the third is 8. So this thing would have jumped all the way up to 8 when I got to x equals 2, or -8 when I got to x equals 2, because if you call it negative x to the third. So this is actually much shallower than what x to the third would have been. But yeah, we're literally just plugging numbers in. It's not that bad, right? Plug numbers in. No, Mr. I'm fantastic. I'm glad you think so, little Mickey Mouse. Do you have questions for me before we move over to the other page? None. Okay. Then I'll scoot that out of my way and go to the other page. Three examples. For each of these examples, we're going to figure out what the degree and the leading coefficient is if it's a polynomial. We will then use that knowledge to state the end behavior if it's a polynomial. If it's not a polynomial, we need to say why. Okay? So again, I'm just going to ask my class, I'm going to say, class, yes or no, polynomial, and you guys are just going to say yes or no. Okay? And if the answer is yes, then we will figure out the degree, and we'll determine if that leading coefficient is positive or negative. We will sketch our end behavior, and we'll write that end behavior in limit notation. Okay. So class, yes or no, is this a polynomial? Yes, it is. So since it is a polynomial, we're going to be able to determine this end behavior, and that's going to be based off of the leading term. Class, what is the degree of this polynomial? 4. Those of you that spoke said 4. I agree. This is a 4th degree polynomial. Degree is 4. And that leading coefficient then is obviously a 2. That's positive. I don't even care that it's 2. All I care is that it's positive. Because if I have an even degree polynomial, do my endings point same direction or different direction, class? Same. Okay, only 4 people answered me that time when I said class. We're going to have to get better at that, because that's one of the things that made you highly successful in the last chapter, was actually interacting with me. Anyway, because it's an even degree polynomial, my endings point the same direction. Class, both up or both down? Both up. Positive people smile. Actually, I need to get some paper under here. The pen doesn't want to work very well on the desk. There you go. Both up. Let us write our end behavior using limit notations then. That's left. That's up. That's right. That's right. And that's up. There it is. I forgot to write that this is an even number. Because for now, all we care was whether was it even or not. When we have more knowledge, that 4 will also tell us, the fact that it is a 4 will tell us more. Because if it was a 6, they still would have been like this, but the 6 would have told us something different than the 4 does. We'll get to that later. Okay, class, I'm looking for all, well, there's supposed to be 30 of you, but it looks like I got, what, 3 people absent? I want all 27 people to speak to me, okay? Class, what is the degree of this polynomial? Did everybody say 4? Oh, not everybody said 4. A couple people said 5. The degree of this polynomial is 5. What happened? It's not in standard form. The exponents did not count down from biggest to smallest like they were supposed to. But that doesn't change the fact that this is the leading term. It's written out of order. So this degree is 5, which is odd. Don't worry, it happened in first period also. Like everybody said 4. That's why it's in the notes. That way you get used to seeing, well, what happens if it's not out of order? Because it's not always in the correct order. And that leading coefficient, I circled it. I think it's obvious that it's negative. It's a negative 4. So since it's not even, the endings don't go same direction. I think that's obvious. This is one up, one down. Kind of like, and it doesn't make it to video because I'm doing it with my hands, but it's kind of like, they call this the in-behavior dance in mathematics, where your teacher gets to do these things with their arms. It's called the in-behavior dance, and there's like these and those. There's all kinds of wild stuff called the in-behavior dance with these arms. So the 3 people that aren't here and had to just watch the video, you just missed out on me looking like a goofball. More than normal, okay? But don't I look odd when I've got one hand up and one hand down? Isn't it kind of funny to say it that way? So I don't feel odd. Okay, so yeah, it's odd. That means one up, one down. The real question is it downwards overall or upwards overall? Class, downwards or upwards overall? Downwards overall. Good, because we've got this negative thing here. We're going to have a left up, right down situation, which has an overall downwards trend. Uh-oh, squeeze my negatives out. So as I head to the left, going up, and as I head to the right, going down. There it is. I got left up, right down. Oakley dokley. Questions on those two before we do the third one? Which is actually all I got to in period 1, but we're going to do the example after that in the video. That way I can at least tell period 1 that they were slow or something. I don't know. I like to poop on people sometimes. It's funny. Okay, this last one. Class, 27 voices. Is this a polynomial? 27 people did not answer me. So we'll do it again. Class, is this a polynomial? Yes. I'm still not getting 27 people. I'm going to start calling on people that I see whose mouths don't move. And they'll be on video having to speak to me one-on-one. So we'll try it one more time. Make sure that all the people around you are saying something and are not too busy on their phones or things like that. All 27 voices. Class, is this a polynomial? Yes. Okay. Most people said yes, but a couple people said no. This is not a polynomial. But why? Because that is a negative exponent. That makes it not a polynomial. This term is negative 3x to the negative 1, which breaks the rules. You must have positive whole exponents if you have a variable. So this is not a polynomial. And since it is not a polynomial, we are not going to attempt to use any rules for figuring out what its in behavior is. Bonus example D. F, G, H, J would be the next one. J of x. Is this a polynomial, class? Class, is this a polynomial? Okay, 2 people. We'll wait. Maybe people are writing. It's fine. We'll wait. Here's what I need. I need 27 voices because I'm looking to hear if I have a mixed bag or not. If you guys hide in the silence, or even if you hide in the voices that do talk, you're basically hoping you get a poor grade. Let's try this again. Class of 27 voices, is this a polynomial? Mixed bag. Okay, and that's what I expect to hear. Mixed bag, and that actually sounded like about 50-50 split. This is not a polynomial because this is a fractional exponent. You must have positive whole number exponents. So this is also not a polynomial. That was a bonus example. Negative exponent, fractional exponent, not polynomial. So here we have a cubic. Here we have a cubic. We should already know which way the endings point. This is an odd degree polynomial. So endings same or endings opposite, class? Endings opposite. Upward trend or downward trend? Downward trend. We already know that the endings of this graph look like this. But that's all we know. What we're going to do now is plug these numbers in on our calculator. I needed to have made this much wider than I did, so I'll have to actually do the work out here. We're going to plug them in on a calculator and fill this out. And you know what? I just realized there's no way I'm going to get that done in the time remaining in this class period. So we'll just have to hold on to our pants on that one, and we'll finish this on Monday. For now, I thank you for being good little robotic nerds.